Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for calculus students and it's a video on optimizing using exponential and logarithmic functions. Specifically, it's from section 8.4 in the textbook, page 321. So if you look at question number 2, it's the equation from part C. And so here's what's happening. So question 2 says to use the maximum and minimum algorithm to determine the absolute max and min for the functions given in question 1. So if we look at question 1 gave us this function as part C. And the original question 1 said to find max and min by graphing. We're not going to do that. We're going to find max and min using the algorithm. So the algebraic algorithm for finding max and min, we need to find the derivative of the function. Use the derivative to find the critical values. That's of course making the derivative equal to 0 and finding the x values that satisfy, because that would represent turning points on the function. And then once we find the critical values, we need to test the original function value for the endpoints of the interval and also any critical values we found that are within the interval. So obviously step 1 is we're going to take the derivative, so let's go ahead and do that. So here is the function, and I just want to make sure I have the pen set up right. So what I see when I look at this function is that it's obviously made up of two functions multiplied together. So the first function x plus 2 and the next function is e to the exponent negative 2x. So I'm going to use the product rule. Oh, I need to set that somehow. We're going to use the product rule here. So let's go ahead and take the derivative. So we need derivative of the first. So obviously derivative of x plus 2 is 1. Derivative of the first times the second plus the derivative of the second. So base e, the derivative is exactly what you see, and then the derivative of that exponent. And so that's the derivative of the second, and then times the first has to be inserted here. So derivative of the first times the second plus derivative of the second times the first. And obviously in order to do anything like get full marks for the derivative or find critical values, we need to do some common factoring. So I'm going to now factor out e to the negative 2x, and that leaves me with 1. And then here I would have negative 2 times x plus 2. And I'm just going to continue and make that bracket a little nicer to deal with. So it's 1 minus 2x minus 4. So this would be e to the negative 2x. And it would be it would be negative 3 minus 2x. And I'm just going to go all the way and factor out a negative, because I like to do that. And there we go. So there is the function, the derivative of the function, my apologies, in fully simplified and factored and ready to go form. So now I need to find the critical values. So we set it equal to 0. Let me change the thickness of the pen. Obviously I need to find a way to make that default. So we set the derivative equal to 0, and then we solve for x. So again, what we like to see, the reason why we factor is to produce two distinct things multiplied together. So that means that if either of those things is equal to 0, we have a true statement. So that means either negative e to the negative 2x equals 0 or 3 plus 2x equals 0. Obviously there's no solutions here because there's no real number that put in the exponent would make this a true statement. But over here, yay, a little bit of nice friendly math. An x value of negative 3 over 2 makes this the true statement. So there's my critical value, and so it's about negative 1.5, we know that. And so if I look back at the original question, negative 1.5 does fit into my interval, which means I have to do 3 tests, negative 4, negative 1.5, and 4. So let's go ahead and test those critical values to find the maximum and the minimum. Boop, boop, boop. Okay, so the function again was here. So it was x plus 2, and then e to the negative 2x. So we're going to test negative 4. So if we sub negative 4 for x, we get e to the da-da-da-da. So calculating this all out, beep bop boop, I get about negative 5,962. If I test the critical value of negative 3 over 2, so subbing that in, negative 3 over 2 plus 2, and then e to the negative 2 times negative 3 over 2. Calculating that out, I get, well, I mean, you know, just because I want to be able to show you good stuff here, this actually works out quite nicely to be an exact expression, and certainly for next year you want to get used to writing exact expressions. Now if I were, this is roughly 10, just to calculate it and compare it. And then I have to test the other upper endpoint, which is 4. So subbing 4 in for x, I get, well, in exact form I get this, which is approximately a small little baby number like that. So when I look at this, where are the maximums and minimums? So obviously the minimum is about -5962, right? That's a pretty small number. And that occurs at x equals -4. And the maximum is about 10, but I'll write the exact one just because I like to be fancy. And that occurs at -3/2. Okay, so again, it's just optimization the way we've always seen it, which is where we need the derivative to find the critical values, and then we test critical values in the interval plus the endpoints of the interval. Just the only twist on it is that we are now able to take the derivative of logarithmic and exponential functions. Okay.